so much easier than doing the 2D with reflex. Yeah, we had kind of talking to the Marla people about how you charge for it, because it's like more than 100 times faster.
Yes. Yeah.
So do you charge 100 times more for it, right? But then it's processing wise so much faster. Yeah, I don't know. Okay, should we kick off?
Yeah, probably. Okay, so I'll need to enable the microphone. There we go.
Perfect. Hi there, everyone. Thanks very much for joining us for the next instalment of this semester's archaeology seminar series at Flinders. It's fantastic to see so many people actually in the room and online as well. I'm really delighted today to be stepping in for John McCarthy as host. John, I think, is about halfway across the Nullarbor on his way to fieldwork. But I'm particularly thrilled to present Marc Young's work. Marc's doing some just fantastic research and has been spending 12 hours a day, 7 days a week inside the microarchaeology lab on the SEM doing this stuff. And I have to admit, when Marc came to me to propose this project, I knew absolutely nothing about this research area, and anything I've learned since then has been from Marc. So this is really exciting to see a student, and particularly an honours student who's only halfway through, come up with a really innovative research question, develop the methods themselves, and then come and present it in our seminar series. So Marc, great work getting here, and really looking forward to your presentation today.
Alrighty. So, my name is Marc Young. Today I'm going to be talking about my research, which is a direct comparison of protocols for extracting Younger Dryas magnetic microspherules. So first I'm going to start off by explaining what the Younger Dryas is. It's a 1200-year cooling event spanning from about 12,800 years ago to 11,600 years ago. It was first recorded by Scandinavian paleobotanists in the 1890s in Danish peat bogs, and they named it the Younger Dryas because of the Dryas octopetala, which is a tundra flower that thrives under glacial conditions. Obviously, during this time, there was a massive resurgence of this flower, and that's where the time period got its name. So at the onset of the Younger Dryas, there was rapid atmospheric changes that took place in less than a year. This is recorded in ice cores and lake valves, and the temperatures caused by this atmospheric change took about 100 years to kick in, and they fell by approximately 8 degrees Celsius in central Greenland in the space of 100 years. Now you'll notice at the end of the Younger Dryas, temperatures plummeted by 10 to 12 degrees C, and that was much more rapidly within the space of 10 years. So an average rise in temperature of 1 degree per year in central Greenland. The onset of the Younger Dryas inspired the movie The Day After Tomorrow, wherein a YD-like rapid cooling event occurs in modern times. So was the Younger Dryas normal? Well, if you look at the history of extreme events in the ice record, and if you just look at the temperature swings, you'd probably say that it looks pretty normal. However, if you look more closely, in both the northern and southern ice sheets, a large methane perturbation occurred. It was roughly, looks a bit higher down the south, but in the north it was about 480. It was about 680. It plummeted to 450, and then as the Younger Dryas ended, it rose back up to 700. Now, you'll notice that in the north, these extreme events have some sort of methane signature, but in the south, it's more muted. So, yet the Younger Dryas one is almost identical in the curve there. So, also at the time, atmospheric CO2 didn't follow the trend of the methane. It instead increased steadily during the duration. And you'll also notice that at the onset of the Younger Dryas, there's a major radiocarbon perturbation recorded in tree rings in both the northern and southern hemispheres. So whatever occurred at this time, it introduced a lot of C14 into the atmosphere. Additionally, wildfire patterns leading up to the Younger Dryas are unique amongst 19 previous Dansker-Oeschger cooling events and 6 Heinrich events. Those are the extreme events I was pointing to earlier. So it's quite unique. And then we have all of these yellow lines here represent previous Heinrich events in the last 80,000 years, while the Younger Dryas in red occurs at the peak of precessional insolation, which means solar radiation is at its highest peak at this time, and you would expect that a 1,200-year cooling event wouldn't be possible with the amount of heat coming in from the sun. So, yeah. So then we also have significant cultural and environmental changes unique to previous events. So in the USA, the Clovis culture, the Magdalenian culture in Europe, and about half a dozen other cultures around the world all experienced decline or reorganization around this time. Major megafaunal extinctions occurred at the onset of the Younger Dryas. And none of these occur on the previous extreme events that we've just been through. And something else that is so often taken for granted that I've almost never heard anyone talk about it. They say, oh, what makes the Younger Dryas so unique? Well, both the geologic and the cultural timescales change at the end of the Younger Dryas. The Pleistocene transitions to the Holocene, the Paleolithic transitions to the Neolithic, right at the end of the Younger Dryas. Not at the end of previous interglacials, not at the end of Heinrich events. At the end of the Younger Dryas is when we see all these changes. It all ends with the Younger Dryas. In the blink of a geologic eye, the world became a drastically different place. A place where humans were suddenly at the top of the food chain. Immediately following the YD, humans changed from hunter-gatherer societies to sedentary agriculturalists. They developed megalithic architecture and many other major technological milestones. So, in 2007, a team of 26 multidisciplinary scientists proposed that all of these changes that we just talked about were forced by a cosmic impact event. They present evidence in the form of a peak in magnetic grains, magnetic microspherules, iridium and nickel anomalies, which are typically associated with cosmic events, radiation anomaly, charcoal, aciniform soot, polycyclic aromatic hydrocarbons, carbon spherules, glass-like carbon, fullerenes and extraterrestrial helium, and then all of the aforementioned events, including the rapid melting of the ice sheets. Some prominent authors on this paper include Professor Wendy Wolbach, who is a leading geochemist on the KT boundary wildfires, Paul Majewski, who's a glacial geochemist and plotted the original Greenland ice core data, James P. Kennett, he's a pioneering paleoceanographer and he co-discovered the Younger Dryas in marine cores, Ted Bunch, an astrogeochemist, he's an expert in impact materials and a former NASA section chief, Richard Firestone, he's a nuclear chemist, a group lead at the Isotopes Project at Lawrence Berkeley Labs, and he literally wrote the encyclopedia on radioactive isotopes. And John Erlandson, he's an archaeoecologist at the University of Oregon's Natural History Museum. So, I'm just going to pivot quickly and delve into microspherules a bit. So, what we see on the left here are microspherules ranging between 25 and about 50 microns. They were all found in the one study for 3 different sites. And these other pictures are also from the Younger Dryas boundary from other sites. Of particular interest, this image here. So you can see that while some of these are textbook spherical shapes, there are others that are dumbbell shaped, some that are teardrop-like, and some that don't look spherical at all. So what are these doing here? Well, in particular, this dumbbell one here, it was originally a spherular, but it was spinning as it went through the air. And as it began to cool, it differentiated itself. So it went to separate, but it couldn't quite separate before it cooled. And that's the reason for that type of morphology. And this one here, the teardrop shape, if you imagine a raindrop falling, it becomes like a teardrop. But if hail hits the ground, it's spherical, isn't it? Usually. So any kind of liquid that cools quickly, freezes or quenches, forms these spherical shapes. And typically, depending how fast they cool, they exhibit these dendritic surface textures that are indicative of a rapid crystallization during the cooling process. So these are spherules from a different study, not at the Younger Dryas, and these are cross sections. So these are what they look like inside. You can see the textbook dendritic patterns here, and I don't really know how this stuff forms, but it's definitely impact spherules. So let's see. So there's 2 main types of microspherules that formed at the Younger Dryas boundary. One of them originates from the ablation of the parent body as it was flying through the atmosphere. So molten material flies off and cools rapidly before falling to the ground. And as this molten material is falling, it decelerates, and any homogeneous chemicals inside, like a lead spot or something, it can actually be ejected from the spherule as it falls. And this is one of the reasons for like this type of crater formation. I mean, this can happen when 2 spherules collide, obviously, but that's the kind of thing that happens as it falls through the atmosphere. So the second type of spherule is formed from terrestrial material that's caught up in the impact plume. This is demonstrated with a nuclear blast here, but it's essentially the same process. Environmental grains, just normal grains from the ground, they are brought up into the superheated plume of ejecta and plasma, where they are vaporized and they condense into spherulitic objects. They undergo several phase changes. If there's a high iron content, sometimes it can come out of the middle and form a shell around the object, which is cool. And often they have high silicate content because it's basically just the material that was picked up from the ground, melted, and then splattered everywhere. So these are typical surface morphologies of impact spherules. They can form polygonal-like structures. They can form fish scale-like structures where you can almost picture the spherule flying through the air and like cooling in waves like that. This brain-like texture is dendritic crystal structures cooling on the surface, similar with this skein texture. And often they can be mixed. So this one is a mixture of polygonal and skein morphology. And often they can be crossed, and this is indicative of surface flow, more than likely, I would say. So, and now spheruleal geochemistry. The Younger Dryas spherules are quite unique among previous impact spherules. So here we see, this is the typical composition of a cosmic spherule. And while there's a pretty good overlap in some of them, they all seem, most of them seem distinct from those. Down here we have anthropogenic spherules. These are formed during industrial processes like welding or forging, any high temperature activity that we do. And you'll notice that the aluminium here is times by 10 and the phosphorus is times by 10. So while it might appear that these spherules are more like anthropogenic spherules than others, the fact is they don't have much phosphorus, so they're always going to skew more down to this corner. Likewise with volcanic, some of the spherules overlap with volcanic, but most of them are distinct with high iron content. And here we have maps of typical terrestrial sediments. The C, Q, P, and B stand for different types of mineral compositions of rock. And you can see these are the Younger Dryas spherules, and they inhabit, they share this area quite well with all nuclear blasts, impact proxies, clay, silt, and mud, and metamorphic. So what this is saying is they're mainly terrestrial in composition, so combined terrestrial sediments, I guess, more so than cosmic material. Now, at least 3 localized ground zero impact sites have been identified at the Younger Dryas. So the first one here is Abu Huraira in Syria. And then we have Blackville in South Carolina and Melrose in Pennsylvania. Now, these spherules here were formed during a nuclear blast that was detonated on an iron tower. And as you can see, the internal structure and external appearance are very similar to spherules taken from these sites, which strongly indicates this is the kind of event we're dealing with here. So, yeah. So back to the Younger Dryas. So this is the extent, about 100 sites, or more than 100 sites, spanning 5 continents, have all produced impact proxies at the Younger Dryas onset. Some of the sites, like down here in Wonder Crater in South Africa, they only have a platinum anomaly right now, but more work is being done there. And you'll notice that Asia and Oceania aren't on the map because they haven't really been studied much, if at all. So the Younger Dryas black mat, this is a several centimeter thick layer that manifests at over 80 sites throughout the Western Hemisphere, mainly in North America, South America, and Europe. And contrary to what some people might think, it's not a burn layer. It's the result of 1,200 years of algal, organic-rich wasteland after the catastrophe happened. And the impact evidence is found directly below the black mat. Here we see charcoal, carbon spherules, glass-like carbon, aciniform soot, and nanodiamonds, tiny little diamonds that formed during the impact event. And of course, magnetic microspherules. So, we've already discussed the megafaunal extinctions. So, almost all of these species, up to 50 species larger than 50 kilos, went extinct at the onset of the Younger Dryas. These bears and a couple of like camelids and llamas and stuff, they're under dispute, but there is evidence to suggest that they also disappeared at this time. Now this mammoth here, this is Big Eloise. She was found at Murray Springs, and she was fully articulated except for her back legs. She was undisturbed in her final resting place after she fell to the Clovis hunters that killed her. One back leg was found next to a hearth, The other back leg was a short distance away. And she'd been completely untouched by scavengers, but she was draped in the black mat in direct contact with the cosmic material, which stained her bones black. And this is taken to represent the day that the cosmic impact event happened. So if you picture Paleo-Indian hunters sitting down to their campfire, getting ready to tuck into a nice mammoth leg, and then all of a sudden, the global impact event happens and they're interrupted. They can't finish their meal. They can't finish butchering this mammoth. So in 2021, the latest study on the megafaunal extinctions from the Extreme Events Research Group at the Max Planck Institute, they used a new method that overcomes chronological uncertainties inherent in radiocarbon dating. And they find that the extinctions closely correlate with the Younger Dryas onset and a human population decline, suggesting a common cause. So at the very least, mastodons, saber-tooth, and sloth populations did go extinct at the onset of the Younger Dryas, while there's still questions about others. So, synchronous vegetation change. All over the world at the onset of the Younger Dryas, vegetation dynamics changed significantly. So here we have a very high resolution record from Europe. There's about a 9-year uncertainty in this. So we can see major changes in the number of total trees here, a massive drop. And also likewise quite a large drop in betula and a slight rise in pine. And a steady rise in Poaceae, whatever that is, starting at the Younger Dryas onset, and this is Northern Europe. And then we have Eastern North America. We can see even more drastic changes at the Younger Dryas onset. Massive spike in pines, massive spike in pines throughout almost all of these sections. Birch and spruce, elm and sedge, they all experience major dynamic changes at the Younger Dryas onset. Likewise in China, some of these records aren't as extreme as the other ones, but this one in particular down here has, I know the lines are a bit thick on this one, I probably should have made them thinner, but you can see massive drops and massive spikes in this record, and less extreme ones throughout the other records. And then in South Africa, typically it's thought that the Younger Dryas cooling didn't make it to the southern hemisphere, but it clearly manifests in the Wonder Crater sediment profile. And you can see, likewise, like everywhere else, massive drops, peaks, immediately following the onset of the Younger Dryas. So now we come to the extraordinary biomass burning. Now, this was a 2-part study in the Journal of Geology. In part 1, they analysed ice core data. And this is an ammonium signature, which is textbook related to biomass burning. And you can see the largest spike in the last 120,000 years right at the onset of the Younger Dryas. And it matches up nicely with other biomass burning aerosols like acetate, oxalate, and formate. They all have massive spikes at the onset of the Younger Dryas. Now, part 2 was looking at marine and terrestrial sediments. So all up, they looked at 152 sections, ice core, marine. These are the results from 10 sites. And then this is the ocean, an ocean core. Now, you can see the large spike at the Younger Dryas there, but there's also a massive, massive spike here at 50K, which doesn't show up in ice cores or anything, so who knows what this is. But without that, this is the largest event in the last 400,000 years, well, 350,000 years of records here. So, the findings of this study, they find that biomass burning at the Younger Dryas onset appears to be the highest during the latest Quaternary. Wildfires rapidly consume 10 million square kilometres, or 9% of Earth's total terrestrial biomass, which is more than the KP impact. and the associated burning products that were ejected into the atmosphere essentially caused an impact winter, which led into feedback mechanisms, and itself could have caused the cooling at the Younger Dryas. It doesn't need to have been a meltwater pulse into the oceans. So another interesting feature of the Younger Dryas onset is a global platinum anomaly. Now you can see this is where the platinum peaks, and there's nothing else even close in the 400-year, 300 years there. Obviously, that's not particularly high resolution, but it gets better. And this was then confirmed. This was 2013 that was found, and then in 2017 there was 11 or 12 archaeological sites that were examined for platinum. Almost all of them correspond very nicely to the termination of the Clovis culture and the onset of the Younger Dryas. It's always found almost directly above the final Clovis remains. This was then corroborated in a lake core from South Carolina, and then it was picked up all the way in near Antarctica in Patagonia in Chile, and then also in Wonder Crater in South Africa. So the distribution of the platinum is global in nature, suggesting some kind of atmospheric dispersal. So as I was talking earlier, we have at least three ground zero sites. One of them is the Epipaleolithic village of Abu Huraira. Now, some of the earliest evidence of domestication of wild grains was found here, but the practice did not continue past the Wadi onset, and archaeologists at the time considered this a failed experiment of farming, perhaps. But we now know that the likely cause of this was that the village was destroyed by a cosmic impact. It was then abandoned for the duration of the Younger Dryas, the 1200-year period, before it was reoccupied. Now, all the major hallmarks of the impact event are found here: the spherical peak, the nanodiamond peak, melt glass, and carbon spherical peak. But also we have exotic melt materials from a direct contact with the impactor. So here we have Libyan desert glass, which is formed from a well-accepted airburst event over the Libyan desert. This is the stuff that Tutankhamun had artifacts made from, the Libyan desert glass, meteoritic glass. And we find identical materials at the Abu Huraira site, in addition to other high-temperature melting proxies. Now this is very small, very magnified evidence that this was definitely formed in these type of conditions. Basically, the thermal pulse from the airburst is what made these at over 2,200 degrees Celsius. There's no other natural process that makes temperatures like this, and it's well accepted that the people at this site certainly did not have the technology to make fires this hot. They didn't have forges or anything like that. So the only possible cause is a direct impact airburst event. And this is an artist's rendition of what it might have looked like for one of these Epipaleolithic hunters as they saw their home destroyed. So what happens in an airburst event? Well, it entirely depends on its size, the speed, the density, the composition, and the angle of approach of the object. And this can lead to a wide variety of different scenarios. But the one I'm about to show you simulates a Tunguska-like airburst. So an object the size of this room enters the atmosphere at about 30,000 kilometers a second. It leaves a superheated plume of ejecta and plasma in its wake. Eventually, it's overcome by the rapid deceleration as the atmosphere piles up in front of it, and this causes it to detonate. The thermal pulse from this detonation is brighter and hotter than the surface of the sun for a few seconds, and it scorches and melts anything in the line of sight, primarily the ground surface, but anything really. It can reach up to like 15,000 degrees at some points of the airburst. It's actually crazy. On occasion, this plume can actually reach the ground, and that's when like severe destruction takes place. And the worst part is these don't leave a crater. So basically, the only evidence that these even occurred are microscopic or very small trace evidence that isn't immediately obvious if you were to travel to the location and look. So that's why these events are by far the most common. Like, these happen literally every day. It's just like they're too small to make it down, so they detonate in the upper atmosphere. So the most famous airburst in recent times was the Tunguska airburst in 1908, wherein a 50 to 60 meter comet fragment detonated about 10 kilometers up in the atmosphere, projecting 15 megatons of energy down in its shockwave. That's about equivalent to 1,000 of the Hiroshima bombs. 2,000 square kilometers of forest were flattened, and these events are expected to take place with a 2 to 500 year frequency. In 2013, a 20-meter main belt asteroid exploded over Russia, releasing about 30 times the Hiroshima bomb's energy. It resulted in 1,600 hospital visits and 12,000 broken windows on 1,000 damaged buildings. So other historical airburst events. Over Brazil in 1930, there was a series of 3 airbursts ranging from 1 to 3 megatons in the space of about 30 seconds. There were many eyewitness accounts of this event, and it's confirmed with seismographic data. In 1976, a meteorite detonated over Kirin City in China. About 100 fragments rained down, ranging from half a kilo to 1,700 kilos. So you wouldn't want to get hit by that one. And then in 1490, a similar event occurred, but up to 10,000 people were killed by falling meteorites. And that's according to the official history of the Ming Dynasty. So those records are very reliable. And I've taken the destruction radius of the Tunguska airburst and I've superimposed it roughly over Adelaide. It's probably not exactly to scale, but it's very close. And you can see that the orange limit here is the range of tree fall caused by this detonation. So basically all of Adelaide would be destroyed if it were a direct hit. So there are several potential impact scenarios for the Younger Dryas boundary. One of them is, it's almost certainly a multi-impact event, but how many is the question? So between dozens and thousands of airbursts and impact over much of the world. Potentially it took place over the space of a couple of decades. One here, one there, so on. The geochemical signatures suggest it's likely cometarian origin. As you can see here, this is the surface of a comet. It's quite Earth-like. There's cliffs, there's rubble piles from debris it's collected in its journey. And because it's constantly accreting material, it becomes like a rubble pile with a widely heterogeneous chemical composition. So anything it sweeps up, it incorporates into itself. So they'll potentially impact into the northern ice sheets, but this isn't required. And unlike with the Alvarez team at the KT boundary, there may be no crater to find. This is the Willamette meteorite. It's the 9th heaviest meteorite ever discovered. It weighs 14.1 metric tons. And it traveled from Canada down to the Willamette Valley in Oregon aboard an iceberg. This iceberg was floating in a mega flood of glacial meltwater with flows exceeding 1 million cubic meters per second, which is 30,000 Olympic swimming pools every second. If you picture this kilometre-wide flood water choked with icebergs, chunks of ice, as this iceberg ran aground and began to melt, it deposited this meteorite among granites and basalts from Canada, which is where we get its origin from, where it sat for the next 12 to 16,000 years. There's no date on when this fell. Chemically, it doesn't match the Younger Dryas, so, but it's obvious that this hit the northern ice sheet at some point, was entombed in the ice, and when the ice sheet melted down, it was sent away. So the most likely scenario, even though there's no direct evidence of it, about 30,000 years ago, a giant comet over 100 kilometers in diameter entered the inner solar system. It became trapped in a resonant orbit with the Sun and Jupiter. And once it was secured in its orbit, it began to disintegrate. Today, up to 88 comets have been linked to this original event, and they're all out there making their own way. And Earth crosses this debris stream twice a year. And during these crossings, it's essentially like strapping on a blindfold and crossing a highway. If you cross the highway at 2 a.m., you're probably pretty safe. You're not going to get hit by anything, really. But if you cross the highway at peak school pickup time, then you're going to take some damage. And that's what we think happened at the onset of the Younger Dryas. This would have resulted in the scenario that most makes sense for the evidence that we find. So the Tunguska event that I just talked about was also occurred at the peak of the Beta Taurids on June 30th, which leads many to, and it also had a similar trajectory. So it's more than likely that the Tunguska object was from the Taurids. In 2018, a 31-kilometre wide impact crater was discovered under the Greenland ice. Early simulations suggested that the impact occurred into up to 2 kilometres of ice. This is based on the hydration of melt impactites and the distribution of ejecta. So there isn't much of an ejecta field, so an impact of this nature would be expected to leave ejecta quite a long way. But there's no such ejecta to be found, so being cushioned by an ice sheet would be one explanation for the reason we don't find ejecta. The oldest ice in the crater dates to the onset of the Younger Dryas. While this isn't a smoking gun, it's anomalous, and it suggests that there's a strong possibility it was formed at the Younger Dryas onset. Furthermore, impact scorched carbon from Pleistocene conifers that lived between 2.4 and 3 million years ago have been found in these impactites, which suggests that it occurred after 2.4 to 3 million years ago. Additionally, the ice is currently responding to remnant geothermal heat emanating from below it. It's figuratively still smoking, okay? So the subglacial water down there is from melting with contact with the bedrock. And geomorphologically, it's pristine. It has a very intact central uplift, very robust rim, and there's minimal erosion, which is not something you would expect if there's millions of years and trillions of tons of ice bulldozing it constantly. But it was recently dated to 58 million years, just 7 million years after the dinosaur-killing asteroid, when there was nowhere near close to being any ice on Greenland at all. So this raises a lot of questions. Shortly after it was discovered, a second impact crater called the Patterson impact crater, it's about 34 kilometers in diameter, was discovered. It was thought to be about 100,000 years old, based on just tentative estimates, I guess. And you'll notice that it's upstream from Hiawatha. You see these flow lines etched into the bedrock from the glacier. The glacier's flowing out this way. Now, it's possible, I see it as a possibility that this is the crater that was 58 million years ago, or there's plenty of other craters under the ice that would date to that time. So it's possible that this material has been dragged by the glacier into the Hiawatha crater, and that might explain all the anomalies along here. So, to summarize the Younger Dryas impact, since 2018, I've been working with the Comet Research Group to compile a comprehensive bibliography. So far, out of 163 papers on the subject, about 100 support it, and there are about 60 that are critical of it. And of the conference abstracts and posters, there's about 60 supporting and 15 critical. And anyone can read any paper at the click of a button. You can watch a chemical professor from University of Edinburgh dissect each paper, examine the evidence, and critique their conclusions. So this brings me to my project. For my project, I'm going to attempt to replicate the YD magnetic microspherules at the Younger Dryas boundary. I'm going to extract spherules from samples and use them to test protocols from relevant studies that have produced conflicting results in the past. So I'm going to use the spherules that I extract, insert them into sterile sediments with a known magnetic grain and microspherular quantity, and use each protocol on those samples and see how many spherules each protocol produces. So it started in January 2022. There was a landmark publication. James Lawrence Powell is known for his systematic reviews of geoscience issues, including anthropogenic global warming. He identified that the Younger Dryas impact hypothesis may have been prematurely rejected, and he identifies an early study as a major factor in the widespread rejection, and he compares the Younger Dryas impact hypothesis to previously other prematurely rejected theories. So what did this paper do or find? So they examined 7 archaeological sites, and they they were unable to find any significant spherular peak at the Younger Dryas boundary. Now, in that paper, they actually admit that they didn't take a single date to identify the Younger Dryas boundary. It was all assumed or based on other proxies. So that it is possible that they didn't even sample the Younger Dryas boundary, or they located the wrong horizon. But there are several issues with their protocols that suggest it could be because of the protocols they used. So in 2012, Lecomte et al. Successfully replicated the microspherular data. They found 260 spherules at Topper, where Surovell found 0, and they were looking at the same sized magnetic fraction. And they also found very abundant spherules at Blackwater Draw, another site, and these are some of this. These are the sum total between all 3 papers of spherules they found. And these are SEM micrograph images of some of the ones they found. Now, Lecomte et al. Identify 5 potential errors made by Surovell that may be responsible for their failure to replicate these results. So this is a table comparing the protocol variables between the 3 studies. This is the original one here. This is the Surovell one, who report they attempted to follow Firestone's protocols as closely as possible, but you can see very clearly that they deviated in almost every way. So they used samples half the size. They did way more extraction than they needed to, which confounded their results. And most importantly, they failed to size sort. So I'll get more into this later. So deficiency 1. At Topper, Surovell took a 10 centimetre thick sample, while the average samples collected by Firestone were 2.3 centimetres thick. Now, the thicker your sample, the wider your layer is between 1 and 5 millimetres thick. So the thicker your sample, the more you're diluting the spherules, any possible spherules that might be there. And you can see the average samples collected by Surovell were 5 times thicker than Firestone's. Deficiency 2, inadequate aliquot size. So after the extraction of the magnetic fractions, you divide them into smaller aliquots, and then you look at those aliquots. So Firestone looked at aliquots of 100 to 200 milligrams in size, while Surovell looked at 10 to 40 milligrams. Firestone often examined the entire magnetic fraction divided into these aliquots, while Surovell did not examine any entire magnetic fraction. So essentially, if Surovell examines 10 aliquots at 10 milligrams, that's the equivalent of 1 aliquot from Firestone. And if you're only looking at 10 aliquots out of your sample, it's possible you might not find a single spherule in those 10 small aliquots. Now, logically, larger aliquots would make it more difficult to find spherules because you've got more detrital grains that you don't want blocking the spherules. But I'm going to be testing this using a grid system with randomly selected squares. And I'll be counting the number of grains in each square and trying to quantify how difficult it is to swap a microspherule. Now, deficiency 3 is the size sorting of grains. Now, if this was 1 millimeter, this is what 150 microns looks like. Now, let's keep in mind that the average size of spherules that Lecomte found is 50, so a third of this. So if you're trying to look for grains this size, and you're having to look past grains this size, you're going to have a lot of trouble trying to locate these grains, aren't you? So Surovell and Firestone examined a magnetic fraction of approximately the same size. Firestone found almost 100, Surovell found 0. And Lecomte labelled this a major deficiency. Now, deficiency 4, perfect sphericity. Firestone found a lot of spherules in his original paper, but they only published images of 4 of them. Now, you'll note that the ones circled in green are indeed perfectly spherical, but the ones in red are not. They've got little pits in them or little bumps on them. And these would have been discarded by Surovell. If he found these, he didn't count them because he was too discriminatory with his spherical characteristics. Now, it's funny because he consulted with the guy who found the spherules in the Firestone paper, and he told them, he sent them images, reference images, where only 2 spherules were perfectly spherical, and yet he decided to still discard them. And this was labelled a major deficiency. So deficiency 5 is no electron microscopy. So when you find a spherule under optical, it looks pretty crappy. You don't have much resolution or detail. All you can really see is the spherical shape of it and maybe some reflectance, right? So this is what it looks like. This cluster of spherules looks like this under electron microscopy. Now, Surovell only used optical to look for spherules. So even if he did find any, he would not be able to confirm that they're from an impact. This one here is one that I found. It's a framboidal pyrite, and it's formed by diagenic and biotic processes. It's not formed by impact processes. And this looks identical under optical to this one here, which is a textbook impact spherule. Now, without SEM, you can't tell the difference between these objects. So It's noted that Surovell did find some spherules, just not in the YDB layer, and these are probably what he found, these pyrite framboids. Now, there's two parts to this project mainly. One, I'll be using the most up-to-date 2022 protocols from Lecomte et al. I'll be looking at 3 Younger Dryas boundary sites from the US. And I'll be trying to replicate the magnetic microspherules results there. And then for part 2, I'm also using those same protocols on a single sample that was sent from a unpublished suspected ground zero site in New York. And I'm going to use any spherules I take out of there to plant in the manufactured samples and use these 3 protocols on the samples and quantify the differences in the results. For the most part, all of the extraction protocols are identical. Like the steps are identical. So we take a neodymium magnet, run it through an aqueous sample, extract the magnetic portion, divide it into aliquots, place it on the slide for analysis. But, as mentioned earlier, each step has variations in, I suppose, variables. So it's expected that, just looking at these changes now, it seems obvious that this is why they couldn't find them, but it could be because they didn't sample the Younger Dryas at all. So, and I should have mentioned that these results have been replicated half a dozen times since by independent teams, so they're certainly there. And size sorting a sample or doing longer extractions doesn't add material to your sample. It only helps you extract material that's there. So to claim that not finding the spherules is evidence that the impact didn't happen, as Surovell et al. Did, it just doesn't fly logically. So I've done about 250 hours of microscopy work looking for spherules, and I've got some preliminary observations. It's clear to me that spherules can vary in size. One of the critiques from Surovell is that Lecomte was looking at a different size portion than Firestone, so any spherules it did find weren't comparable, which just simply isn't true. Based on the formation processes, they can form at any size, basically. I've found spherules ranging from 5 microns to 60 microns, and they all, most of them exhibit features typically associated with high temperature impact events and rapid quenching. So it's also very difficult, laborious, and time-consuming work. That's very clear to me. I've noticed that some aliquots produce almost no candidates while others produce abundant. There was one aliquot that I looked at, I didn't get a single spherule. And then the very next one, I found about 10 spherules in an hour, and then I found that this large cluster that I've been showing you as well. So, yeah, that speaks for itself, really. So Lecomte uses a more powerful N52 magnet instead of an N42. And I've noticed that this has the potential to increase the unwanted grains because presumably any spherule is going to be pretty highly magnetic. So it'll be picked up within the first few passes, while subsequent passes will collect less magnetic materials over time. So some of the materials I have are almost pure quartz with like a tiny little magnetic inclusion in them, and that's enough for the magnet to pick it up. So spherules can still be obscured by larger grains, even in this narrow size fraction. Between 20 and 63, they can still be obscured. So I can't even imagine what Surovell was trying to accomplish with 1 millimeters. Surovell's longer extraction produces larger magnetic fractions, same kind of concept with the more powerful magnet, which increases the number of unwanted grains, which is further exacerbated by the lack of size sorting. And framboids are easily mistaken for YD spherules under optical and require SEM for identification. And that's it. Thank you very much. Are there any questions?
Yeah, thanks very much for a great talk, Mark. I'm sure we have some questions either from the audience or from Collaborate. Well, let me ask one to kick it off.
Sure.
I mean, I think your discussion about the lack of sites found so far in the Southern Hemisphere is really interesting and something with great potential for further. You might need to use them. Oh, sorry. Yeah, I'll use this one, Dale.
Yeah.
I think that your discussion about the lack of sites in the Southern Hemisphere is really interesting. If this is an airburst event, and there isn't necessarily an impact crater, I mean, in that case, is it likely that we will find sites in the Southern Hemisphere? And if not, does that, like, if we look for them, we don't find them, what does that say about the theory in general?
Yeah, so presumably you would expect that they would be present, especially in sites where sediment input is quite good and constant. Anywhere with discontinuities, you might find that the Younger Dryas has been washed out. But I mean, if you look where it should be and you don't find it in the Southern Hemisphere, then either the impact field didn't extend to the Southern Hemisphere, there's some sort of astronomical phenomenon with the angle of approach of the meteors or something like that, or the event didn't happen, I guess. But that still doesn't explain why all these other things have been found. Yeah. Anyone else?
In the samples you were just saying before, you were saying like some had none at all and some had many. Do you think there's any reason for that? It's just completely random?
Yeah, so it's possible there could be a reason. There could be some sort of phenomenon occurring with the magnet or the way you extract it that bunches them up. I've noticed that static electricity is a factor that you're going to deal with. I don't know how that would affect magnetic objects over non-magnetic, but mostly the fact that some aliquots contain spherules and others don't is just down to pure chance. Or there were some there and I just didn't find them. So that's always an option too. Yeah. Anyone else?
So have we just not been looking for them in Southern Hemisphere?
More or less. So following the early rejection with the Surovell paper, a lot of prominent impact scientists no longer took the theory seriously, like Christian Kerbel, he's a top impact guy, like he's vehemently against the theory. Mark Boslow, an airburst guy, he's vehemently against it as well. To the point that he's accused one of the main guys of running a widespread scientific conspiracy to commit fraud out of his basement, like salting samples and sending them all over the world for analysis. Like, that's the kind of like criticism we deal with. So yes, to answer your question, more than likely it's because of the early rejection, but it's just possible that no scientists in the Southern Hemisphere have really seen it as a pressing issue that they want to research.
I mean, I think the point needs to be made, Mark, and jump in if I'm wrong with this. But for example, if you had a drill core that went over this section, you're looking at a sedimentary outcrop, you're not going to see this probably visually in the Southern Hemisphere. There's no evidence for this black mat or anything in Southern Hemisphere sites. So it does require getting level right, taking the samples in there.
But if you were to review the archaeology in Australia anyway, there's a lot of things that are going on between 10 and 12,000 years ago. Changes and inversions.
Yep. Now there is a paper from John Tibby who titled the Younger Dryas in Australia or something, and he finds that there wasn't really much of an environmental effect in Australia, which I find strange because there is in Chile, in Patagonia, and there is in Wonder Crater in Africa. So there could be some kind of climate parameter that doesn't allow that kind of thing to filter into Australia, but I can't think of anything reason why. Yes.
So the black mat you're describing is a algae buildup.
Yes. So it's basically.
Has that type of algae been found in Australia?
I don't actually know what type of algae it is. There are papers that characterize that. I haven't looked into that too much.
Different algae in Australia that
Potentially. I think, the algae could be around, but just not suited for the environment, so it doesn't proliferate. But like in a post-cataclysm wasteland environment, that's the perfect conditions for algae to proliferate, I would say. In the moist, lots of rotting organic matter around, that kind of thing. Now, we've got a question from Joanne online. I'm going to try and see if her sound comes through. Do you want to ask, Joanne?
All right, can you hear me?
Yes.
Hey, that's pretty amazing. All the way across the planet, I get to talk.
Hell yeah.
Okay, so regarding your evidence of the Younger Dryas boundary in Australia, are there any known like burn layers such as you would see in the American Southwest or in the Netherlands and Belgium, like the Oslo Horizon? Is there anything known like that?
If it exists, I don't think it's been synthesized into a paper that describes it as being such. It's possible that there's these kind of horizons out there around the Younger Dryas in Australia, but I don't know if they've been explored as being particularly relevant or not. Would you guys have you guys seen anything like this?
In a micro level,
Yeah.
well, no, but
No, in terms of the black mat. Yeah.
not that I can think of.
Yeah.
I think, and Darren knows much more about this than me, but particularly in the northern Australian.
Okay, so it's kind of hard to hear what your audience is saying.
Yeah, so I'll just pass the mic.
Thanks for the question, Joanne. I'm sort of on the fly here, but my sense is in a lot of northern Australian sites, the preservation of organic material back to 12,000 is pretty bad. So if it was there, it probably wouldn't survive into outcrop.
Well, but in the Netherlands, you've got the cover sands, and there is a distinctive burn layer there that is preserved in some places. So maybe you'll find it in Australia or New Zealand.
And that's rich in nanodiamonds and wildfire material, isn't it? The Oslo Horizon?
Yes, it is.
Yeah.
And it has fused quartz grains and melt glass in it. It's pretty interesting.
Wow. Yeah, there's been a bit of work done in Europe to actually distance the Oslo Horizon from the black mat. They've jumped through all sorts of hoops to do it, but all the impact proxies are there, and it dates to about the right time. So,
Right.
Yeah, that's it. Thanks for that, Joanne.
Okay, good job. Good job, Mark.
Thank you very much. Anyone?
Just a comment. At least in Southeast Asian sites that I've been looking at that time, so far as the archaeology can say, there's no clear evidence of the Younger Dryas.
Yeah.
And so, like even in my primary site for the PhD, Tampaling, I was trying to see if I could possibly identify it through the microstratigraphy.
Right.
But then it's really a long shot to say that there's something, evident in the sediment inside the cave,
Yeah.
evident of climate outside, unless you do like isotopes.
Yeah, right.
The guys who did like Myanmar working in Thailand say that there's no clear evidence. But just as an added.
So for the online people, Vito's just commented that there's also very little evidence for the Younger Dryas onset in Southeast Asia where he specializes. So, yeah, no worries. All right, if there's no more questions, I'll hand it back to Ian. Thanks, everyone, for attending, especially those international viewers.
Thanks very much, Mark, and thanks everyone for coming along. Same time next week. I'm not sure if we're in person, but we'll certainly be online. So thanks everyone for your attention. Thanks, Mark. Great talk. Yeah.
Because I know with Clarkson
Thank you.
changed to Silk Creek.
Yeah.
There are things like that.
Yeah.
I think across around the country. I mean, not
Nice.
got plenty of Blake to do and everything like that, but if you wanted to,
Yeah.
Thank you very much.
in Australia, that's,
Great. Thanks for coming along there.
you know, it's between 10 and 12.
Yeah.
You just have to look at that in a whole bunch of sites.
I mean, Mark and I thought, Mark was originally thinking about working on some of the Timmy's cores and John Tyler's cores and looking at that, which I think actually is quite, based on what you've done here, would be quite a viable project now to look for these things with the SEM rather than doing the platinum.
I want to, I mean, it's all out there. I just need to look it up.
Yeah.
But I want to look at the vegetation change in Australia as well, around the Younger Dryas, because I think, I mean, the level of change around the world is so extreme.
Well, that's the thing. How can Australia not? Okay, it might not have spherical things,
Yeah.
but it's going to manifest itself in something.
I mean,
else, like,
at least the platinum would expect it to be here.
look at all the rock art.